I'm Peter Sandusky. This is a demonstration lecture to support my application for a lectureship at Cal Poly San Luis Obispo. And the topic of the lecture is chemical equilibrium. Now, in previous lectures, we've been discussing phase equilibrium. And I'll remind you that when you have two phases in equilibrium, for instance, if you have some liquid water and you have it contained in a flask that's initially evacuated, at some point the liquid water will go into an equilibrium state with water vapor, so that the partial pressure of the water vapor will be given by the Clausius-Clapeyron equation, will be just a function of temperature. And if you look at the phase diagram of water, we have temperature versus pressure, you have water vapor and liquid water. The line dividing the two phases, the liquid and vapor phase in the temperature and pressure plot, are the set of conditions where liquid water and water vapor are at equilibrium. Okay, so saying that we have attained an equilibrium state, that there's an equilibrium between liquid water and water vapor, is actually to constrain other variables, in this case temperature, pressure, to a certain sets of values. And the same thing is going to be true with chemical equilibrium. Now, this is a dynamic equilibrium, okay? So that while liquid water molecules are constantly going into the vapor phase, and vapor phase water molecules are constantly going into the liquid phase, what we can say is that at equilibrium, the rate at which liquid water molecules go into the vapor phase and equals the rate at which gas phase water molecules go into the liquid phase. Okay? So it's a dynamic equilibrium. And all of these things will also be true with chemical equilibrium. So let's consider a generalized chemical reaction. Generalized chemical reaction where we have A moles of substance A reacting with B moles of substance B to give C moles of substance C and D moles of substance D. Okay? Now we begin our analysis of equilibrium by writing a algebraic construct called the reaction quotient. Okay, as you know, if you have x over y, that's the quotient of x divided by y. So the reaction quotient is the product of the concentration of the products raised to their stoichiometric coefficients, okay, divided by the product of the reactants raised to their stoichiometric coefficients, like this, okay? Where these small case letters, of course, are the stoichiometric coefficients. Which you determine by balancing the chemical reaction, all right? So when we write this out and we can fill in the concentrations for the different reactants and products, but this reaction quotient doesn't necessarily have any particular value unless we, and the reaction quotient, we could symbolize that with a Q. That doesn't necessarily have any particular value, numeric value, unless we say at equilibrium, the system is at equilibrium, okay? So again, this would be a dynamic equilibrium where the rate at which A and B are reacting to go to C and D equals the rate at which C and D are going back to A and B, okay? In that case, at equilibrium, the reaction quotient expression takes on a specific value, which we call the equilibrium constant. Okay, and this is a specific numeric value for a specific reactant at a specific temperature and pressure. And the need to specify temperature and pressure will become obvious when we discuss this in terms of thermodynamics. Okay? Now still, though we can say when our reaction is at equilibrium that it's going to have a specific value for its equilibrium constant, that doesn't mean the concentrations of the reactants and products are constrained to particular values, okay? So let's take the case where we have our generalized reaction and we set all of the stoichiometric coefficients to 1 just to simplify things. So our equilibrium constant would then be the concentration of A times the concentration of D over the concentration of A times the concentration of B. That is the concentration of C times the concentration of D over the concentration of A times the concentration of B, because the stoichiometric coefficients are all just 1. Okay? And this is going to have a specific value. Let's say 4. Okay? But there are infinite number of different combinations of the concentrations of C, D, and A, B that can multiply and divide together to make up 4, okay? So for instance, you could have the concentration of A1, the concentration of B1. These would be like molarities. They don't have to be, but they can be molarities. Moles per liter would be 1 mole per liter for A, 1 mole per liter for B, 4 moles per liter for C, and 1 mole per liter for D, and that would all multiply together to give you the equilibrium constant of 4. On the other hand, you could have 1, 1, 2, 2, or 1, 1, 1, 4, or 0.250111, or 1.25011, or you could have 0.5, 0.511. Those all would give you the same equilibrium constant. So the concentrations of reactants and products at equilibrium depend not just on the value of the equilibrium constant, but also on the history of the reaction mixture. Okay, the initial values of reactant product concentrations when the chemicals were mixed together before they came to equilibrium. How the equilibrium was established, what chemicals were there when they were initially mixed together. That, along with the equilibrium constant, will determine the equilibrium values of concentration. Okay. Now, to illustrate this, I'd like to go to discussing an actual reaction. So, if we consider, for instance, N2O4 going to N2O2. Now N2O4 as a gas is a reddish brown, whereas NO2 is colorless. And these two molecules, they're emitted in car exhaust, and they're important components in air pollution. Okay. Now, in analyzing equilibrium conditions, equilibrium concentrations of reactions and products, we set up what we call an ICE table, an initial change equilibrium table. Okay. So, and for this reaction, we have only two chemicals, dinitrogen tetroxide and nitrogen dioxide, one reactant, one product. Okay, and so I stands for initial concentrations. And so we would just have to, if we're doing an experiment, we could just pick initial concentrations. Whereas maybe if we were dealing with an environmental problem, we'd measure some initial concentrations, okay? But at any rate, let's suppose, just for this demonstration, we pick an initial concentration for dinitrogen tetroxide of 1, let's say 1 mole per liter, okay? And an initial concentration of NO2 of 0 molar, okay? Then the change is the molarity of N2O4, excuse me, the molarity of N2O4 that reacts to go to equilibrium, that reacts in going to equilibrium. Okay, and let's just call that X, because that's what we're going to have to solve for. Okay, so if the change in the concentration of N2O4 is X between the initial conditions and the equilibrium state, then what's the change in NO2? Well, it would be 2X. Now we would write this X actually technically as with a minus sign, because we're losing N2O4, but we're gaining NO2. Okay, so the change in N2O4 is minus X. The change in NO2 would be plus 2X. Okay. Now at equilibrium, conditions we started out with 1 molar N2O4, and we reacted X molarity of that, so we'd have 1 minus X. Okay. For NO2, we started out with 0 molarity of NO2 and reacted 2X, so we'd have 2X. Okay. Now our equilibrium constant, okay, which is a value that we could establish experimentally for the system, of course, is going to be the concentration of NO2 raised to its stoichiometric coefficient, which is 2, over the concentration of N2O4 raised to its stoichiometric coefficient, which is 1. Okay? Now we can then substitute in for these concentrations the x's. Okay? That gives us 2x squared on top, and in the denominator 1 minus x, like that. Okay? Now, where we're going with this, okay, we set this ice table up based on some initial conditions, based on the change, which is really derived from the stoichiometry of the balanced reaction, okay? And then we write out our equation for our equilibrium constant and substitute in the values of the concentrations in terms of this x, in terms of this quantity, which is the amount of one of the reactants has to change, the concentration has to change going between the initial conditions and equilibrium. Okay, then we can solve for x in terms of KEQ, which we know, okay, and then we can determine the equilibrium concentrations from the bottom line of the ice table. Okay, so that's what we're doing here. Now, rearranging this a bit, we've got KEQ equals 4x squared over 1 minus x, bringing things around there. That would give us KEQ minus KEQ x equals 4x squared, or rearranging again, give us KEQX, that would give us 4x squared plus KEQX minus KEQ equals 0. Now you'll notice what we've done here is we've put this into the quadratic form. So we can solve for x using quadratic form, of course, is ax squared plus bx plus c equals to 0. We can solve for possible values of x as being minus b plus or minus square root of b squared minus 4ac over 2a, right? Like that. And so if we do that, and using a, so we could substitute in here then the b's, the a, b's, and c's here, where from this equation a would be equal to 4, b would be equal to KEQ, c would be equal to minus KEQ, okay? And using the quadratic equation, and KEQ, as it turns out for this reaction, is 0.0059, and you have to always specify the temperature at 298 K, yeah, so 25 degrees. And when you plug this number, the KEQ number, in to the quadratic equation, you're going to get an x value of 0.0 0.153, okay. Then using the bottom line of the ice table, you can see that at equilibrium, N2O4 will be, the initial value was 1 molar, but we reacted 0.153, and so that gives you the final concentration of 0.847, and the molarity of NO2 is going to be 2x, and so that's 2 times 0.153, which is 0.306 molar. Thank you for your attention.